Hello, we are Team Prometheus. In light of the 2013 discovery of the potential oceans on the surface of Jupiter's moon Europa, we decided to design a research base to house scientists beneath the ice caps. We created a brief outlining the requirements and assigned each section to a different team member. We decided to make it for 24 inhabitants, but also that it should be durable enough to sustain many cycles of research teams. The base should be completely self-sustaining, allowing for food production, energy generation, and atmospheric regulation. To allow for data collection, the brief also includes robotic submersibles and even theorizes what life could be found in Europa's oceans. We decided the base should not contaminate its surroundings in any way.
Our settlement will consist of 4 domes along with a large central communal dome. We have chosen to use a hemisphere design as this is the most effective at equally distributing outwards pressure. Extrapolating data from the International Space Station allowed us to calculate the minimum volume of the biodomes to be 2,800 meters cubed.
The dome shall attach to the bottom of the ice sheet using vacuum suction. This will be supplemented with large gas-filled balloons, assuring the biodome stays immersed just below the surface.
The dome's material will consist of a silicon iron and titanium alloy. This has been chosen due to a strong chemical resistance to sulfuric acid at all concentrations up to boiling point. This alloy has been treated in a process called passivation and then anodized to increase its acid resistance further. This will be then coated with a fluoropolymer of tetrafluoroethylene, as this is completely unreactive with sulfuric acid and all other acids likely to be found in the ocean.
As we shall be attaching to the ice using vacuum suction, there will be no harm to the ice caps. The structure is also chemically inert and will not react with the surroundings, therefore leaving the environment unaltered.
To get the dome structure to Europa, we must first escape Earth's strong gravitational field. To do this, we found our rocket must travel at 11.2 kilometers a second. Using Tsiolkovsky's rocket equation, it was calculated that to transport a 1,000 kilogram payload, we must use 28,500 kilograms of fuel. Once we have landed on Europa, it will take years to acquire any tools or equipment from Earth. As a result, 3D printing will be a necessity in the biodome, allowing us to print useful tools such as this 3D printed wrench.
To maintain a constant internal environment, electrolysis of water will be used in conjunction with the Sabatier reaction in burning methane. This will not only act as a closed system but also generate energy.
We will use aeroponics and hydroponics to grow parabolic flowers. This will help us to avoid the issue of not having access to soil and instead utilise the extent of ocean available. This will help us be more efficient. The parabolic flowers use retroreflection to help us focus the light on the interior of the plant. This will maximise the energy available.
When in space, due to a lack of gravity, sinuses get clogged in the nose and in the taste. Therefore, we'll be using red cabbage, which is grown in a quick and easy 33 days and provide a powerful taste for the astronauts, also providing them with a variety of flavours.
In order to safely explore Europa's oceans, we propose a 3-metre-long torpedo-shaped submersible with a 0.3-metre diameter. It will be powered by a lithium polymer battery, which is more stable and efficient than the lithium ion. This would power 1 main thruster propeller and 2 pan-directional thrusters. It could have several sensors: pH, temperature, pressure sensor, obstacle avoidance sonar, a hydrophone, ground stereo camera system, ground camera, and a docking camera. It would communicate with fibre optic port for fast data transmission of large amounts of sensory data and raw film. It would also include Intel processors, 1 for navigation and all sensors, but 1 dedicated for film processing. And of course, a dedicated one for handling instructions and output of information for its autonomous missions.
The sub can also move with a fibre optic tether for live HD footage of the hull for diagnosing problems. It also connects with Wi-Fi for longer range, but only for non-autonomous exploration. The proposed submersible is also capable of taking small samples. It uses a microfluidic device smaller than a human thumb, with a special filter to trap tiny microorganisms. The shell of the submersible would be a titanium silicon alloy, 7 millimeters thick and cylindrical. This will distribute the pressure evenly across an already strong surface. The case would, of course, have an extremely thin treated strip of silver running across the top and bottom in order to effectively transmit the radio signal.
The lack of sunlight penetrating the ice could cause there to be little skin pigmentation in Europa's life forms. Therefore, it's likely microorganisms would use chemosynthesis to release energy for growth. It is also possible that some of the life forms could be similar to tardigrades, methanogens, Sassanidium caldarium, due to their resilience to some of the most extreme conditions. In order to find potential life, CO2 detectors will be used.
Thank you for listening to our presentation. This is an example of how ingenuity, innovation and technology can be used to establish a biodome on Europa.